we left off. Okay, so last time this was the problem that we were doing and the class ended. So let's look at it from the beginning, that we have a bridge rectifier and it consists of 4 ideal diodes, A, B, C, and D, as shown. So you can see that this is your setup. You already know right off the bat that if you have a bridge rectifier connected in this way, it will always produce it produces a full wave rectification, right? But then again, that's not you. It's always better to check what is happening. So you can see, you can check it by saying that first the current goes in this direction. It's an alternating current, so it goes in both the directions. What happens when it goes in this direction? It goes here, and unfortunately it cannot go to this part of the diode, so it just directly goes to the resistor like this, over here, then comes back over here. Actually, it would when it goes over here, it would travel over here, and if you change the direction, make it opposite, so then you can see that it goes over here, follows this path, this one, and then again goes through the resistor in this path. Now, an alternating supply is applied between terminals X and Y. The variation of how the potential varies with respect to time is shown in the figure, right? So again, you can see that the figure is a full wave rectification, as you would expect. And let's look at some of the values over here. So it's starting from 0. There is no damping in the graph, as the amplitude for every peak, the peak value is always a fixed value of +4 volts. So this +4 volts is the peak voltage given over here. Okay, so the load has a resistor 2700. Let's see what we want. We want to determine the mean power dissipated in the resistor R. So we know that the mean power that is dissipated in your resistor, it is given as the square of mean voltage divided by R, right? Okay, so what is mean voltage? Mean voltage is the peak value of voltage over under root 2. But now you can see that if I square this thing, then there is a square over here, which becomes V0 square over 2. So let's put this thing back in your equation. So you get V0 square over 2, that's the mean squared of voltage, and then there's a divided by R, so you add that R over here. So now it's straightforward. The peak voltage from the graph, from this figure, is 4 volts, and the resistor is also given, so this would be 4 volts squared divided by 2 times the resistance was 2700 ohms, right? So this gives you 2.96 into 10 raised to power minus 3 watts. Was that clear? Any questions?
No, sir.
Okay. All right. Okay. On figure 6.1, draw the symbol for a capacitor connected so as to increase the mean power dissipated in the resistor. So we want to connect a capacitor to increase the mean power that is dissipated in the resistor in the form of heat. So how can we increase mean power? Can you tell me how will the mean power increase?
Connecting the capacitor in parallel.
Okay, yes, exactly. We'll connect the capacitor in parallel in the circuit, parallel to the resistor R. And how does it help to increase the mean power dissipated?
Sir, by the soothing effect.
By the smoothing effect. So what's happening in the smoothing effect? The sum of the voltage drop decreases and it stores. So this is just it's not asked, at least not in this part. Maybe in the next part they have asked for it, but so we'll draw it. So let me use another color. So what happens is your cycle follows the same path, but now because there is a capacitor, the voltage does not drop by a lot or does not drop to zero. In fact, it drops by a slight amount, and again it starts to go back up, and then again it drops by a slight amount. Okay, so this is not so something like this, and then it again goes back up, and of course then this pattern continues, so on. So what's happening over here is instead of voltage being completely dropped to zero, if I take the average of this rectified, of this smoothed graph, the voltage would be higher compared to the average voltage of the original graph, because the original graph is always going to zero, then again rising, then again dropping to zero, and then again rising from there, while the smoothed graph does not drop to zero, only drops by a little amount, and so it only has to go a little bit up to recover that, and then again it drops by a very small amount. The small drop is again because the charge or the energy is stored inside the capacitor, and if the energy is stored, that just means the potential difference or the voltage is stored. So on this figure, where should I draw the capacitor? Again, it should be in parallel with the resistor R, right? Okay, so that's clear.
Yes, sir.
Any question? Okay, all right. So let's go. The part C, the capacitor is now removed from the circuit. Okay, so you're removing the capacitor. Diode A in figure 6.1 stops functioning. So now what's happening is the capacitor is also removed. So there is no smoothing going on. And the diode A is also removed or it stops functioning. So that it now has an infinite resistance, which means it's not working anymore. So draw a variation with time t of the new potential difference across the resistor R. So we want, first of all, if you go back to this thing, they said diode, what was it, diode A? Diode A. Diode A has stopped working. So if diode A has stopped working, so let's say that there is a break in the circuit over here. So the current, if I take this path of the current, it cannot go in this way. It cannot do that. Why? Because there is no closed path for it to follow. The circuit is broken over there as diode A is not working anymore. It cannot go to this path as well because this diode, although it's working, but its direction is in the other way. So the current, if the current flows in this particular direction, it does not flow through the resistor at all. Does that make sense? Is that clear?
Yes.
Okay. So that's one direction. Now let's check the other one. The other direction of the current, when it flows like this, it's going to go to this this part over here, and From B, it will also go up to this point, this one. Now it cannot go in this direction because the circuit is broken over there. But it has another path, which is this one. So it follows this path and it flows through the resistor R. So in one direction, the current is not flowing through the resistor, and on the other direction, the current does flow through the resistor. What type of a graph would you expect for that?
Sir, can you explain the first current direction flow?
Yeah, of course. So the first one, from starting from X, it goes up. It cannot go to A anymore because they said that diode A has stopped functioning. It's not working anymore. It has infinite resistance, meaning that the current can never go in this path, as the circuit is broken over there, or you can say that the resistance is infinite. It cannot also, so if it cannot go over there, then of course there is no way that it will be going in this direction. But for D, if this other path where the diode D is connected like this, you can see that the direction of the diode is in this way, which means it's going to allow this direction of current to flow through. However, in this case, what's happening, the current is going in this way. So this diode restricts that flow of the current as well. Now there
In
is
this path,
no
no
other.
flow is there.
Sorry, again.
In this path, there is no flow of current.
There's no flow of current. As it cannot go through, again, you should understand why. Because it cannot go through A, there is infinite resistance over there. It cannot go through D because the diode points in the opposite direction of the current. Current is going this way, but diode is pointing in the opposite way, which means, remember, wherever the diode points, that directional current is allowed to flow in that direction. In this case, it is the opposite of that, so this current will not is not allowed to flow. So it's not going to flow through the circuit, right? So is that clear?
Yes, sir. Sir, in
Okay.
the second direction,
Yeah.
it will return from D.
In the second direction, why it's going to go like this? It will go. Okay, so second direction, it's going here like this, right? It encounters this point. Now it can either go over here or over here. But if it goes over here, this one, if it goes over here, then again the same story. The diode points in the opposite direction of the flow of the current. So it's not allowed to flow. What about in this direction? In this direction, you see that, yes, of course, it can flow because the diode is in this direction, upwards, and the current is also flowing in that direction, in this direction, right, across the wire, which means that the current is going to go up until this point. Now, from this point, it has again two choices, just to go in this right path or go in this path, left one. It will not go to the left path, this one, because again, diode A has infinite resistance, no longer working, so the circuit is broken, current is not going to flow through there. But then the only option now it has is to go through this path, the right one. And when it goes through this path, of course, you can see that the current flows through the resistor R. Okay, so is that clear?
Yes, sir. Sir, the current in this path will return from diode D back to the battery. It will return from diode D.
No, it will not really return back to the battery. The current will not flow at all. The current is, so I mean, it's not correct really to say that the current is going to flow back to the battery, but the current will not flow at all because there. You have to think of it like that. That it's not like the charges that are flowing, they flow and then they see, oh, the path is blocked, okay, I'll go back. That's not what's happening, right? This is just an analogy that we're using, but this is not what happens inside the circuit. If the path is blocked, then the current is not going to flow from the battery. Because when does current flow? When there is difference in potentials between the 2 points, there is some potential difference and the current flows in that case. In this case, it will not flow at all. Okay.
Yes, sir.
Okay. So all right. So again, the question is, what type of a graph are you expecting if the current is only allowed to flow in one direction? There are two directions, right? So only a direction that is working has a single diode connected to it. So what type of a graph do you expect for that?
Is it half-wave rectification?
Half-wave rectification, exactly. So you would have a half-wave rectification. Now, how would that be? So let me use another color. Let's use red. Let's increase the size. Okay. So how would the half-wave rectification be? It will start from here, go until this point, and then it will be 0. Then again, it will go like this. And then again, it will be 0. And then again, it will start. Okay, so is that clear?
Yes.
Okay, all right. Okay, so that does question number 3. Let's move on to this one. We have a sinusoidal alternating voltage supply, and it's connected to a bridge rectifier consisting of 4 ideal diodes. The output is connected to a resistor R and a capacitor C. So this time the capacitor is already connected, and we have a bridge diode, so we have a full wave rectification. And the function C is to provide some smoothing. The function of C, right? C is the capacitor, is to provide some smoothing to the potential difference across R. The variation with time t of the potential difference across R is shown. So this is the graph that you would be expecting normally as well for this type of a circuit. There is a capacitor connected, so you would expect a smoothed voltage graph. Okay, so using this figure 6.2, determine for the alternating supply the peak voltage. Can you tell me by looking at this figure, what would be the peak voltage?
4 volts.
Quickly, 4 volts. Okay, so that's 4 volts. Let's just decrease the size. Okay. Now the root mean square value of voltage. How do you calculate that? V.r.m.s, which is the same as the average value of V. It is what?
1 over the square root of 2.
1 over the square root of 2 times the peak voltage, exactly, right? So the peak voltage is 4 volts over square root 2. This is 2.8 volts. All right. So no questions, right? Clear? Okay. So, okay, now next we have to find the frequency and show our working. Okay, so what would be, by looking at this figure, how can you determine the frequency? First of all, what is frequency? Just write that down, right? Frequency is the inverse of the time period, 1 over the time period, right? So if I can figure out the time period in this question, then I can find the frequency. How do I figure out the time period? I have the graph. So by looking at the graph, what would be the time period of this wave?
Sir, 20.
It should be 20, right? So it starts again, it's starting from here. So the time period is for one complete oscillation, right? So up and down both. But in this case, it is a full wave rectified and it's smoothed as well. But remember, if it was not, the full complete cycle would have been a wave that would be something like this, right? So this would be from here to this point. Look at this when it's at the same height again, which is this one. So over here. So this length will be the time period of the wave. Is that clear?
Can we not measure it from 2 blocks ahead so that it is easier?
Of course, then you can do that. But then if I'm starting from here, then the end point is here. Right? The end point also has to move to the right by 2 blocks. So then this would be 22 and this is 2. So this entire length is the difference between the two. So that's 22 minus 2, which is again 20. Is that clear?
Yes, sir.
Okay. So now we have the time period as 20, but it is, remember, always check over here for the prefixes. So it's in milliseconds, which is just 20 into 10 raised to power minus 3 seconds. So we can put that in our frequency. F is equal to 1 over T, 1 over 20 milliseconds. And this gives you a frequency of about 50 hertz. All right. Now, the capacitor C has a capacitance of 5 microfarads. For a single discharge of the capacitor through the resistor R, use this figure to determine the change in potential difference. So for a single discharge, what is the potential? What is the change in potential difference? So before discharge, what's the potential? And after discharge, what is the potential left or saved inside the capacitor? The difference between the two will give me the change. So of course, before discharge happens at all, the voltage value is maximum, peak voltage, right? As you can see over here, this one. Okay, when the discharge is happening, what is the value of the voltage? The discharge is happening up until this point, and it drops to the minimum, and it's discharged now. Not completely discharged, but it's discharged. And then again, it starts to rise back up. So what is this point? The value at this point when it's discharged?
2.4.
This is 2.4 volts, exactly, right? So we have both the potentials. Before discharge, it's 4, and after discharge, it's 2.4. So the change in potential difference, change in V, is before discharge, 4.0 volts, minus after discharge, 2.4 volts, which is 1.6 volts. Okay, was that clear for everyone?
Yes, sir.
Okay, perfect. Now, next, determine the change in charge on each plate of the capacitor. How can I determine this charge, the change in charge on the plate of the capacitor? Let's see, what do we have? We have the capacitance, right? If you, sorry for that. We have the capacitance, if you read this thing. We also have a change in potential difference. So if they're requiring the change in charge, I know charge is given by the capacitance equation, Q equals CV. Okay, the capacitor is not going to change its capacitance. It's a fixed capacitance of 5 microfarads. So it's a constant. So if the charge is changing, that would mean that the potential difference has changed. So now we have everything. Capacitance is 5.0 into 10 raised to power minus 6 farads. And the change in potential is, as we saw, 1.6 volts. Right. So this would give me the change in charge as 8.0 into 10 raised to power minus 6 coulombs, right? Yeah. Was that clear?
Yes, sir.
Okay. All right. So next, show that the average current in the resistor is this. Okay. So we want to find the average current, I. We have charge and we have the graph, so we can figure out T as well, right? We have the graph. And remember, the average current in the resistor would be coming from when the discharge is happening, right? That's when the current is flowing. So we know that current is the rate of change of charge, dq by dt. This would mean that if I have the change in charge, which I do, which is 8.0 into 10 raised to power minus 6. Now, this change in charge happened over what interval? What would be delta t? This was happening during the discharge is happening. So if I can figure out the time taken for discharge, then I can figure out what this current I would be. So the time taken for a discharge is, if you look over here, at this point it's at peak, and at this point it has dropped to the minimum value, so it has discharged. The difference between these points, this one and this one, is of about, so this is 12 and this is 5. So that's 12 minus 5, this length, which is what, 7 milliseconds. So that's the value of delta t, 7 into 10 raised to power minus 3 seconds. So now you just do the math. This should give you 1.1 into 10 raised to power minus 3 amps. All right, so was that clear?
Yes, sir.
Okay. So there's another part. Use the figure and the value of the current that was given to estimate the resistance of the resistor R. Okay, so the current I, we have the average current. How can I find the resistance? I know that the relation between current and resistance is given by V equals IR. And from here, R is just V over I. So remember, the current is the average current. So corresponding to that, we require the average potential difference. So what would be the average potential difference? Did we compute that? We did, right? The average potential difference is this one, right? Halfway between this curve. So that's 3 volts. Is it 3 or is it 3.2 volts? Does that make sense? So V would be 3.2 volts. The current, the average current is 1.1 into 10 raised to power minus 3. So just put these back in this equation. So you get 3.2 over 1.1 times minus 3.
Sir, where did 3.2 come from?
Okay, again, the equation is R equals V by I. The current is the average current. Remember, that's what we computed. The average current in the resistor is this. So that means that to this there should be corresponding. It should be corresponding to the average voltage, right? So if you go back over here in this figure, what would be the average voltage? Remember, in this graph, for example, if I have this graph, you know what the average of this graph is, right? The average voltage of this graph lies at the center, which is 0. In exactly the same way, if you look at this graph, you want to see what part of it lies above, what part of it lies below, about what line. So if I draw a line at this center, so it's in the center of the part that is up over the part which is down. So you can see every time it's the same part repeated. Part which is up, part which is down, part which is
Sir,
up, right?
we take the average
Yeah.
value of 4 and 2.4. The
Yeah,
highest
you
and the
can do
lowest.
that. It should give you 3.2 volts exactly. Not 2.4, 2.2. 4 and 2.2, right? Because it's ending. The graph is coming to a drop, minimum drop at this point. This point was 2.2.
This point is 2.4.
2.4 is just above that, right? This one. This point. Okay, is that clear?
Sir, is it this 5 box?
Which one?
Sir, from 2 to 4, there are 5 blocks in between.
From 2 to 4, there are, oh, yeah, sorry, my mistake. You're correct, right? So this is 2.4 volts. Sorry. Yeah. So it's okay now. The average potential difference, is it clear?
Yes, sir.
Okay. All right. So this would give you the corresponding resistance of 2900 ohms. So any questions so far from these?
No, sir.
No,
It's
sir.
clear.
Okay. So this worksheet has ended. With this, AC and rectification has also been concluded. Next, we'll start with charged particles, right? We're now going into the realm of modern physics, right? And we'll look at charged particles. We'll look at nuclear physics, quantum physics, and coming out from that, we'll see, we'll dive into cosmology, and then finally we'll conclude it with some practical applications to medical imaging of physics, right? So in the next class, we'll be starting with charged particles.